Hey, welcome back to EECS 370 discussion. Today we're looking at cache-aware programming. And, you might be sitting there after going through most of the semester. If you're like me, you are a computer science major and you're really, really interested in this hardware stuff and you want to start studying that more. But if you're not like me, which is totally okay and really good, actually, you've been wondering, like, why does Michigan require us to take this course at all? And that's what I seek to answer tonight as we give you tips to actually make your programs run faster. If you forget everything else in EECS 370 at the end of the term, we want you to know how to use these hardware concepts to actually make better software as you continue throughout your undergrad degree and everything else that you do with computer science and computer engineering and other fields in the future. Before we get into that, project due dates are upcoming. If you're taking this in the fall 2022 term, project 3 is due very soon on Tuesday. And then the homeworks for the rest of the term are going to be due on Fridays. And then the last project and the last homework will be due after Thanksgiving before we get to that final exam. This is a new discussion for winter 2022. And so that's why I'm doing the recording in fall of 2022, because we've modified some things for this term. But I'm going to go through a few things that you can use in order to make your programs run faster, given the concepts that we touched on with caches in the last few weeks. So the first thing that we can leverage when we're doing our caches is optimizing our array accesses. So a lot of times we're going through arrays. This is something that we commonly do in our programming. And let's look at this array that we have here. So we have some code. We have an int array that has 128 members. And we're doing some operation on every element in the array 5 times. And so you can see how we have our loop. We're going to go through the full array 5 times, 1 for each of our count. And then we're calling this function do something. It doesn't matter really what it does right now, but we're calling this function. And if we think about our caches right now, we know about a spatial locality and temporal locality. And when we run this code, we're going to go through the entire array 5 times and eventually touch each element of the array 5 times. But we can actually improve this code for caching in one really big way. And that is by changing the order of the loop. So we've been going through the array 5 times. And if we go through an array 5 times in our cache, it's very possible that by the time we get to the end of the array, we've removed everything else in the array from our cache. We've evicted everything else because our array is kind of long, it might be longer than our cache. And so we want to find a way to undo that. And so we can do that with our loop reversing. So in the previous code, we had our count loop on the outside, and then our inner loop was actually going through the array. Now we reversed it so that the outer array goes to the loop, or the outer loop goes through the array, but the inner loop now does whatever we're trying to do 5 times. And so that allows us to stay at each element in the array and do our function, whatever it has to be, as many times as we need to with that element, and then we will never need to access it again. And so we won't be worried about it being evicted from our cache later on. And so this is one of the main things that we can do to improve our temporal locality. Our spatial locality is kind of already supplied to us by the array, but this will really help our temporal locality in particular, because we are removing the possibility of eviction for every element when we come back to access it multiple times. So one of the things you can do is reversing loop order. We have seen this on the homework. If you've looked at homework 5, there's probably a question on this. I know there is for fall 2022. Let's say that we have some similar code that goes through an array at a stride. So instead of just going element by element, it goes every, maybe 4th element and then does something. And then it starts back from the beginning. And then eventually it covers all of them. but it doesn't do that in a very linear fashion. So if we had some code like this, we could see that this might mess with our cache a little bit. For example, if we have a block size of 4 and our stride length is 4, we'll go and access every 4th element of our array. But if our block size again is 4, then we'll only access 1 element per block, and we aren't really going to use our spatial locality very well. And so we have ways again to reverse this, and that's by changing these stride lengths. So we really want to use our spatial locality to help us with our stride patterns. So here, another example, if our stride is just 1, that's just like going through the array. On the other extreme, if our stride length is the full length of the array, which here is 128, then that's practically like going through the array linear again. So if we look at this code, offset goes from 0 to the stride length, and then stride goes from 0 to some amount to keep us under the bounds of the array, and it increments by the stride length. And so if we have a stride length of 128, well, offset will start at 0, stride will start at 0, stride plus offset will start at 0, I suppose. And then when we increment our stride by the stride length, well, it's going to go to 128. And so our for loop will exit, at least the inner one. And then we'll increase our offset to 1. And the same thing, access element 1. And so that basically means that this inner for loop is just going to do 1 iteration every single time. So that means that in the end, our double for loop will just go linearly through our array. And so if we have some sort of intermediate stride length like 8, our index will start at 0, as in both previous cases. And then in this inner for loop, we'll add 8 to 0. So our stride length will become, our stride index will become 8. And then we'll do the same thing. We'll add 8, and it'll go up and up and up, adding 8 each time until it reaches 120. And we'll reach 128, and that's greater than or equal to 128. So we'll go back, increment our offset to 1, and start over again. And eventually we'll get through the entire array. So if, once again, we invert the loop order, we get a different access pattern. So if we have that stride length of 8, if we invert the order and fix up a few things in our loop bounds just to make sure everything works correctly, then we'll get a different pattern that might be better for our cache. So let's say once again that our stride length is 8. So we'd start off with stride being 0, offset being 0, and so our first axis would be 0. Then we'd increment the offset on the inside, and so it would go to 1, and then 2, and then 3, and so on until it gets to 8. And then that would be our stride length, and so we'd go back out, and this stride would increment to 8. And then our offset would once again be 0, and we'd access 8, 9, and so on. And that would just eventually be like going linearly through the array. And so if we change that loop order, we're just going linear through the array, and it's no different from going just with a stride length of 1 or 128. And so we saw before that flipping the loop order allowed us to better use our temporal locality. Now flipping the loop order also benefits our spatial locality. And so we get a much better access pattern for our cache. We're less likely to reach any evictions. And so we've optimized this code for a cache. So that's one general thing, flipping the loop order. And so we can use that both for spatial and temporal locality. The temporal locality really affects our counts, and the spatial locality really affects our strides. Let's say that we have some similar code. Let's say let's say that we go with the code from the first slide where we had some index. Let's even go with our optimized code where we were doing the index on the outer loop and the count on the inner loop. So we're going to do something with an array element, and we're going to do it 5 times. Now you might remember from our earlier discussions, I think it was discussion 2, where we talked about how for loops are implemented in assembly code. So we always have some sort of range check. Maybe that's a BEQ to check if our index, I'll just use IDX instead of register for right now, is equal to 0. And if so, we'll go to the end of our for loop. Otherwise, we'll do the stuff inside the for loop, whatever that is. And then at the end, we'll increment our index, IDX. And then we always have this conditional or this unconditional branch to go back up. And so in LC2K, we do an unconditional branch by comparing 0 to 0 or any register to itself. And we go back up to the top. So this is what a for loop typically looks like in assembly code. And here's the end. And so we notice that every iteration, we have an unconditional branch. So every single time we're going to take this branch and there's no way to avoid it. Notice that this top branch is only going to get taken at the end. So that's really not going to hurt us. But if we're thinking about our pipelining that we've now learned about in this course, we know that branches have significant penalties to our CPI. And so they take extra cycles. And so we want to reduce the number of branches that we have in our code. And so if we do what's called loop unrolling, we can transform our loop to remove all these unconditional branches and just serialize the inner loop. So before we had our inner loop where we had our count, and it would do something and it would do it 5 times. Well, that's the same as just calling the do something function with arguments 0 through 4. And so ultimately it will do something with our array element 5 times. It's the exact same code, but now we've removed all these branches because now our code looks something like this instead. Let me use a different pen color. So we can remove this unconditional BEQ, and then we'll do our inside 5 times. So inside, here's time 0, here's time 1, inside time 2, inside time 3, and then 4. And then at the end, we actually have our new end label. And before we get to that, we'll increment our index and we'll have our singular branch. So before, this is really a single layer loop, but we would have a double layer loop. This time, we're just going to have a single unconditional BEQ at the end that will only get taken after we do our function 5 times. And so we reduced the number of unconditional branches at least by 80%, which is really good for us. Now, you might be wondering why we're talking about this with caches, because really the cycle penalty has to do with our pipeline instead. Well, we know that jumping to different parts of code might mess up our cache. If we're at one PC and we're storing everything in our instruction cache in a very serialized manner, we're expecting to go one by one through instructions. Whenever we take a BEQ, suddenly we go to a different address, and maybe that will cause an eviction for us. We don't really want that in our cache, and so instead, if we can serialize the access pattern for even our instructions and treat them like an array, then we've improved our cache optimizations. And so one thing to note is that this loop unrolling really only works if your iCache is big enough to hold all the code to hold these multiple calls to do something, because there are 5 instructions here to jump to that function. And so your iCache has to be big enough to hold all that. Maybe you replace each do something function with a sequence of code that runs a bunch of different instructions. As long as your iCache is large enough to hold that, you've reduced the branch penalties, but everything is still going to fit in the iCache. We don't have random jumps to different places that are going to mess up our evictions. So this is ultimately a good thing for us. So both of the things that we've talked about so far, between flipping the loop order and unrolling loops, these are things that your compiler actually is probably already doing for you. So if you want to learn more about that, you can go take EECS 483. I highly recommend it. It was a very fun class, and I'm in 583 now. If you want to go beyond 483 and learn more about those types of optimizations. But towards the beginning of the class, we learned how to take basic C code and turn it into assembly. And it's really all your compiler does. And so if your compiler can do these things, then we can too. It's really easy. But there are some things that your compiler just can't be smart enough to do. And so that's what we'll cover for the rest of these slides. So one of them is inline functions. You may have recalled from project 3, we've started to introduce some of these inline functions, but we didn't really explain what they were yet. And so an inline function just takes a function and turns it into assembly code and inserts it into your main function itself. And so this will reduce the number of branch penalties because every time we take a jump, it's like a jailer instruction, it has to go to some other PC. And even though we didn't implement that in the pipeline for project 3, you can imagine that if we did, we'd have all these unconditional branches and we'd get to the same number of branch penalties for our CPI that we did for our taken BEQs. And so we want to reduce the amount of branch penalties. Also, if we have really small functions, then the actual function might take fewer or as many or a similar number of instructions to the jump itself. For example, if we have some instruction from project 3 or some function from project 3 that gives us the opcode, we know that that's just right shifting the instruction by 22 bits. We don't really need a dedicated function for that, but it makes our code look cleaner if we have opcode to designate exactly what we're doing every time we right shift. And so if we just replace that with like an LSL instruction in ARM, if we replace the branch with exactly one LSL instruction, then we haven't changed the number of instructions in our main code. We've actually kept it the same, and so we won't hurt our iCache in that way, and we've reduced all those jumps. So they'll actually improve our iCache and our code size. So that's an example where we replace a function with exactly one instruction. We could replace it with 2 or 3 instructions, and hopefully the iCache is big enough to take that hit. And most of the time that's going to be true. But if you ever have a function that's small and can be called a bunch of times and you think it might benefit your iCache to actually put it in the main instead, you don't have to get rid of your function. You can just inline it instead with the inline keyword. Really easy to do. Most of the time, you'll probably also want to put static in front of it so that it doesn't cause any linker issues, but I don't know if that's strictly enforced. So that's inlining. And so to recap, the main idea is that we can replace our function call with a small number of computations in order to eliminate the branch penalty. And so that will be something that might hurt the instruction cache, but most of the time, they're really large enough to take this hit, especially if everything's in serial in the end. That'll help our spatial locality. We can combine our inlining with loop unrolling. And so if we have some sort of inline function, let's say that this do something function that we've been working with is inlined, well, we know that without inlining, each of these is a jump. And so we saw before that we reduced the number of unconditional BEQs by 80%. And so that was good, but we still have all these unconditional branches because that's what jailer really is. It's an unconditional branch to a register address instead of an offset. We still have all these branches, and if we inline instead and replace the functions with whatever they're actually supposed to do, we've eliminated all these jailers. So in the end, we've actually reduced our branches by 90% if we have an unroll factor of 5. If that loop that we had, the inner loop, had a count of some other value, could be better or not as good. But our loop unrolling combined with our inlining is really going to help us by cutting out at least half the branches. And so that's really good for us. And so once again, that's something that your compiler can't do on its own. You have to specifically inline the function because if you don't inline the function, then when you link, the compiler is going to have to make that function available elsewhere. And so it's going to keep that, that function in your text section. But if you inline it, then it'll just stick it in all the parts of main. It won't have its dedicated spot in the text section. So that's why we have to inline, because when we link, it has to be available to other source code files. And so we've eliminated that possibility by making it static and inline. So that has to do with our functions. We can also use smart data structures in order to optimize our code for our caches. This is something that we don't really talk about in each 370 because 281 really focuses on the data structures. We're instead focused more on the hardware and the assembly code and more the instructions. But these things do have to meet at some point. And so let's look at how some of these data structures can affect our caches. So let's consider how we would implement a linked list in C. This should look pretty similar to what we did in X280 in some of the lectures. You'll remember that a linked list, it has some sort of head, so where the linked list begin, and then each element in the linked list has our piece of data, and then it has a pointer to the next piece of data in the linked list. And so that's what makes it a linked list, because each pointer is the link between elements. And so these pointers can point to anywhere, because most of the time we are allocating them from the heap instead of like the stack or the data section. And so our heap has all these different locations in memory. It's pretty large. And so it can be hard to bring the heap into the cache, because with so many addresses, different heap spots could constantly be evicting others if they go to the same set. And our data on the heap tends to be really large also. A linked list in particular, you'll note that if we have both a data element and a pointer, well, that's more than containing just the data element that we would have from something like an array. And so linked lists can be really mean to our caches. And so we would sometimes want to use a different data structure in order to optimize for our caches. But this is not always true. If we have some sort of program where we really need fast insertion and deletion, or maybe if we have some program where we work on just 3 elements of the linked list at a time, and we really hone in on that temporal locality, then our linked list can be good instead. And so we need to be able to balance these things. So generally, if we really iterate the linked list, then it's probably not the data structure for us for this program. An array would be much better. But if we're doing something where we're camping out on a few elements of the linked list for a long time, the linked list will be good for us, especially if we are doing insertion and deletion operations. We can kind of generalize this. We've been talking about the linked list, but there are other pointer-based containers that we have, especially in C++. If you've taken X280 and X281, you'll know all of these. But our trees, so in C++, that's the set and the map. Those are all pointer-based. They have pointers. They're all allocated on the heap with a new keyword. In C, you could implement it with malloc and custom structs like we did on the previous slide. And then we have our list in C++, which is actually a doubly linked list, and our forward list, which is our singly linked list, like on the last slide. Those would be good, once again, if we're sitting on elements for a long time, but they wouldn't be so good for our caches if we're going through all the elements in the data structure. Other index-based containers are going to be much better for our caches. So it's going to contain any sort of an array or vector. Our deck-based data structures and our wrappers to make a stack and a queue. Those are really, really good because the stack and the queue can kind of move along as we pop things from the front or the back and add things to the front and the back. And so it kind of maintains the shifting range of addresses, and that can be really, really good for our cache and minimizing the amount of evictions that it does. And the same thing goes for our priority queue. You might remember that our priority queues can be implemented sort of like vectors. And so the head of the priority queue can be index 0. And then the next two things that can be there in priority would be indexes 1 and 2. And so we can do some math to figure out all the indices. And so if we can keep our heaps in some sort of vector-like structure, then that's going to be much better for our cache. Now you could also implement a priority queue like a tree, and of course that'd be worse for our cache, but I think C++ still implements a heap in terms of a vector. But one of the things, of course, about abstraction is that that could change at any time. So don't always count on that, but it's likely that these things will unchanged. One thing that's kind of mixed is our hash tables. So these are unordered sets and our unordered maps. You might remember that our hash tables kind of start off with a set of pointers. And so each pointer kind of points to a vector of different elements. And that's kind of like our bucket for our hash table. But in order to get to that vector, we have a pointer. And so if we really camp out on a certain bucket for a while, then that could be really good for our cache. Of course, the initial pointer chasing will not be good for our cache. But if we're doing something with our hash tables where we're constantly jumping between different buckets, that could be worse for our cache. And that could probably be actually the worst of all these data structures for our cache if we're doing something like that. This is where iterators can become really helpful for us, since our iterators for our unordered data structures will go through the buckets for us. And so we don't really have to worry about that. And that's actually what makes it unordered. It's really ordered in the sense of what's in each bucket rather than going through each possible key. But again, that's an example of something that can be used the same way in code as a set or a map, as a tree. But the actual under the table, under the hood implementation of these unordered data structures is very different. And so one's better for caches, one's worse for caches in certain situations. So as programmers, we need to know which one is going to be better. All right. So I encourage you to refer to EECS 281 notes. I'm not an EECS 281 DSI, so I would encourage you to refer to EECS 281 for more details on all the exact implementations. But keep these things in mind when you're doing your projects in future EECS courses, or maybe even EECS courses this semester, to optimize your code to run as fast as possible given your cache setup. The final thing that we'll cover today is our struct alignment. This is something that we've stuck with in EECS 280 pretty much from the beginning of the semester. And so this was useful to us when we were looking at the sizes of different structs and how we could access them in ARM assembly when we convert from C code. And we learned at the beginning how to optimize our structs to save space. And so what I want to suggest to you is that this will actually also help us with our time, because when we save space in a cache, that improves our time to access. And so this will be our one problem for today. And so we'll just walk through this to see how that can play out. So problem one, if we have a byte addressable architecture with a 64-byte data cache with a block size of 16 bytes, we want to know how different structs could behave in our cache. And so let's start off by figuring out how many example structs fit into this cache. In order to figure out how many structs will fit in the cache, we have to know what the actual size of the struct is. And so let's start off with that review some of the things that we did on the midterm and calculate the size of this struct. So the first thing I'll do is look through at all our primitives. We have a character, and so that's a 1-byte type. We have a float, which is a 4-byte type. Short, 2 bytes, an unsigned int, 4 bytes, another character, 1 byte, and then an int, which is 4 bytes. And so we know that in the end, our example struct will have to be a multiple of 4, since that's our largest primitive. And so we'll also have to align each primitive to an address that's a multiple of its size. So let's assume that our struct starts on some multiple of 4. And so if we kind of draw our grid, we'll have our character A, And then our float B will have to be aligned to a multiple of 4. And so that means that we will need 3 bytes of padding between A and B in order to align our float B to a multiple of 4. And we have a short C, and we can see that if it starts right after the float, it's already aligned to a multiple of 2. So we don't have to add any padding. But if we add the unsigned int D right after that, then we need to do some more padding. So D is 4 bytes. It will be aligned to an address of 4 bytes. That means that we'll have 2 bytes of padding after C. All right, then we have another character. That's a 1 byte type. And then finally, we have our last int, which is another 4 byte type. So once again, we'll align that to a multiple of 4, and we'll need 3 bytes of padding in between E and F. All right, and in the end, that's a multiple of 4. We can kind of see from the grid. And so let's see, we have 6 rows of 4 bytes each. And so the struct will take a total of 24 bytes. If our struct takes a total of 24 bytes and we have 64 bytes in our cache, we can just do some division here. 64 bytes divided by 24 bytes per struct gets us about 2 and like 2/3 of a struct. So we really can't fit that much in our cache. And so let's move on to see what we can do here. All right. So first, let's go through our greedy algorithm that we did at the beginning of the semester. And let's realign our struct so that it has a minimum padding and size. So remember, in order to do that, we can start with the largest type and then just work our way down. So we can start with the 4 byte data types, our float, unsigned int, and regular int, or signed int. And then after that, we had a short, and then we had 2 characters. And so let's look at what the size of this is now. So if we do our grid again, we have B, which takes 4 bytes, and then D, which takes 4 bytes, F, which takes 4 bytes. Then we have C, which takes 2 bytes. And then we'll have our characters A and E. So we can see that this takes only 16 bytes. And if we remember that our cache was 64 bytes, 64 over 16 is 4. So we can fit 4 structs in our cache now. So before we had, what, 2 and 2/3. And so now we've improved that to 4, which is very good for us. And so if we happen to have some sort of array of example structs and we only had 4 of them, then after our compulsory misses, we would never miss again. But with our old struct alignment, we would have tons and tons of misses after that. So we've improved our temporal locality after that. We can also improve our spatial locality because before we were able to fit just those 2 and like 2/3 structs in our cache. But if we need to access all of them maybe 1 or 2 times and not have a bunch of temporal accesses, then we can, with our new struct, fit them all into the cache and then go back and forth between different of the structs without worrying about them evicting each other. And so we've improved our spatial locality by evicting or by reducing our evictions of different structs. And then also, now that we've reduced the size of the struct, even if we just access one of them, the members of the struct are more likely to be in the same block. So if we had, let's see, we go back to our block size, which was 16 bytes. That before could only hold part of our struct. And so our struct before may have been split out among multiple different blocks, but now our entire struct can fit in just 1 block. And so if we make accesses of different members in the same access to our struct, then we've improved our spatial locality. This is true, by the way, not only if our new struct will fit in just 1 block before, if we had some struct that was split out across maybe 8 blocks, if we can reduce that to just 5, then we've improved our spatial locality significantly since struct members have a higher chance of being in the same block with other struct members. And so those are the ways that we can improve our spatial and temporal locality. All right, so let's see if there's a way that we could improve this better. And it looks like my slide is messed up a little bit. Let's say that we have two scenarios, two possible data structures that were given. Let's say that we have this type separated struct, and let's say that we took the individual portions of an array of structs over on the right here. Let's see, so struct example, let's say that we have an array of 256 of these. Now, on the right side, if we have just an array of structs, each member of the struct is with the other members of that struct. But if we wanted to separate them into different types, so that we have an array of all the floats, an array of all the ints, an array of all the shorts, an array of all the characters, we could do that with the structure on the left. And so we might do this for certain reasons. For example, if we knew that we had some code where on one pass through our array of structs, we only accessed maybe F, well, then there's no reason to bring the entire struct into our cache every single time. We just want to bring all the ints in. So if we bring them in together, that improves both our spatial locality and our temporal locality. Our spatial locality because we're bringing in more actual useful data in one block, and then we're also reducing the chance that we'll evict something important. So that'll improve our temporal locality. There might still be times where we would want to use the thing on the right, where we have just an array of structs. That could be useful if every time we access a struct, we access all of its members. If we tried to do that with the thing on the left, then whenever we access a member, then we would have to make accesses to each of these different arrays instead of just bring the entire struct into our cache at once. So these two things have their different advantages, different situations where we use them. And so this will actually be very similar to the loop flipping that we saw before. This is kind of like doing our strides in a different way, just with structs instead. And so you can use all of these ideas that we've talked about today. They will be great inspirations to write test cases for Project 4. But that's everything I have for today. Catch you next time in each 370 discussions.